My name is Suhairi. I'll be sharing with you the result that we have obtained in the experiment titled, a very mouthful title, Performance Improvement of Optical Fiber Sensor Detection using Bandpass emission filter. So the objective of the experiment is actually to make a comparison between two different detection techniques. The conventional way of detecting fluorescence, which using the intensity-based detection, and also the method of using phase fluorometry, which becoming more popular nowadays in terms of detecting oxygen concentration. And what we are doing was we try to evaluate the performance of the detection scheme if the system is using a bandpass filter and without bandpass filter. The reason for doing that was we were asked by we have another group who's looking into the deployment of such sensor, and they were developing the readout system for our sensor. And one of the problem was they have a very unstable measurement from our sensor. So to compromise, what we do was we perform a test to investigate whether there is a need to use a very narrower emission filter, which indeed in this experiment demonstrated that the system need to have a good filter in order to get a stable measurement. So my role was actually to develop the sensor, and at the same time, our system development guys developed the electronics for the measurement of the oxygen sensor. So before I proceed, just a quick glance of the governing equation in the fluorescence detection. This is the popular established Stern-Volmer equation, where it relates the relationship between the oxygen concentration and fluorescence intensity. If we expose the sensor in an oxygen environment, what we'll see is that the oxygen concentration will slowly reduce, and we can use this Stern-Volmer equation. You plot a Stern-Volmer plot, we will get almost in ideal case we get a linear line, which we can quantify the performance of the sensor with respect to its sensitivity. Another approach is to use a phase fluorometry, where it relates the phase changes in terms of phase changes that actually measure the changes in terms of the excitation signal, which is the energy that we provide to the sensor, and the emission signal that being returned back by the sensor. And as we increase the oxygen concentration, what we will witness is that the reduction in terms of the phase difference. So this is a very important technique, because in the development of a sensor, always the issue of cost and also miniaturization of the system play an important role. So the other group is looking into this aspect, and we are looking into the research aspect. And this is the sensor probe that we developed. We are using plastic optical fiber. Again, it's the cost issue. Instead of using normal glass fiber, this fiber was purchased from Mitsubishi, and we prepared the fiber by terminating it with a connector on one end, and we will cut it at 45 degree on the other end. And at the end of the fiber, we coat the fiber with a material that is sensitive to oxygen. In this case, we are using ruthenium complex dye, which we prepare with a standard way of preparing with a sol gel. And we decode it at a withdrawal rate of 400 millimeter per minute. And this is the problem with fabricating the sensors, that you have to dry it. You have to allow it to dry for a few days before you can use it. So in terms of manufacturability of the sensor, it is a critical issue that people have to solve. So we dry it for 2 days before we test it. And this is the experimental setup, optical setup, where it's a very simple setup. We have the excitation source, the LED source, and being connected to a bifurcated fiber. And this is a sensor. And the sensor is connected back to the bifurcated fiber, and we have these two different measurement technique: the direct measurement, which is the intensity base, and the indirect measurement, the phase base. And the thing that we investigate is actually the inclusion of two type of bandpass filter, the emission filter. One is a broad bandpass filter, and the other one is a very narrow bandpass filter. And we put this sensor inside the gas chamber, and we vary the oxygen concentration through the use of the gas mixer. So once we excite the sensor with this energy at 450 nanometer, the sensor will emit a fluorescent signal at almost 600 nanometer. So this has been detected by the detection scheme. And in this graph, what we can see is that without any filter being used in the setup, we will see that this is the excitation signal, and this is the emission signal. So as we increase the oxygen concentration from 10% up to 100%, you will see the quenching of oxygen. So you can see the reduction of spectrum. So the next step was to include a bandpass filter, a broad bandpass filter, in the setup prior to the detection, still using the direct measurement technique. In this result, you can see that the emission signal has been eliminated, and this allows for a higher emission in the green line as compared to the previous one. Okay, so then we proceed by testing it with a narrower bandpass filter. It's about 25 nanometer bandpass filter, and it responds very well, and you can see that the emission signal has increased tremendously. But we have to quantify whether this relates to the performance of the sensor. So what we did was we plot this Stern-Volmer plot again, and we noticed that there's no significant improvement with respect to the sensitivity and also the linearity of the sensor itself. So having said that, the sensor itself behaves very linear and the sensitivity. So the next experiment is to use an indirect measurement technique, the phase fluorometry technique. Again, the same thing happened here. Initially we started off with using a broadband emission filter, then followed by a narrow band. So this is the result of the test. Without any filter at all, you can see that as we increase the oxygen concentration, the phase changes will reduce, and the narrower the bandpass filter, you can see that the changes is greater. So in the design of the readout circuit from our system development group, they require at least 7 to 8 degree of phase difference. So initially they had problem in getting that phase difference. Normally we get about 5 degrees. So in this setup, we proved that by using a narrow filter, we were able to get at least about 12 degrees phase changes, and it's followed by 9 degrees using a broad filter, and finally only 2 degrees for a system without filters. So again, to quantify this performance, again we plot this graph, and we notice a big improvement with respect to the slope of the sensor performance. This is without emission filter at all, and this is with broad emission filter, and finally this is with narrow emission filter, which indicates that with using by including the narrow inclusion filter, we will be able to improve the performance of the sensor and also the detection scheme. And finally, as a conclusion, as I mentioned, the use of filter in direct measurement does not in any way increase the performance of the sensor in a great way. It just indicates a minimal improvement in sensor linearity and sensitivity, but you can see that there's a significant improvement when we use the phase fluorometry, and also together with the narrow bandpass filter. And this large phase difference is important in order to have a very accurate and stable data measurement for such system. So with that, I